Imagine a tunnel in space that links distant points, a shortcut through the fabric of space-time. This idea, called a wormhole, is a hypothetical bridge predicted by solutions to Einstein's equations. A wormhole connects two separate points in space-time, different locations, different times, or both. Physicists discuss many types, some theoretical, some possibly microscopic, but none proven yet. In this video we will explore how wormholes are imagined, how they appear in equations, and what they might mean for travel and time. We start with simple visualizations, then dive into the physics and the fascinating possibilities. Stay with us. By the end you'll understand why wormholes capture both rigorous science and imaginative fiction. A helpful picture: draw two distant points on a flat sheet of paper. If you fold the paper so they touch, you create a shortcut. That is the intuitive idea of a wormhole. In reality, a 3D space would require a fourth spatial dimension to do the same bending. Embedding diagrams show a throat connecting two mouths. Think of spherical holes joined by a tunnel. One mouth could be here, the other there. Distances outside may be huge, yet the tunnel is short. A traveler inside would move along the tunnel, experiencing local laws of physics as usual. Researchers have even simulated what a traversable wormhole would look like in real settings. Remember, analogies are visual aids. The true object lives in higher dimensional geometry. Behind these images are precise solutions to Einstein's field equations. The math defines the geometry. So, paperfold analogy, embedding diagrams, and the throat-mouth picture. 3 ways to picture a wormhole. Next, how the idea entered physics history, and who gave it its memorable name. History and terminology come from decades of mathematical exploration. Keep these images in mind as we track the story from 1928 to modern theories. Now the story behind the name and the ideas. In 1928, Hermann Weyl proposed tube-like structures in space-time, though he did not use the word wormhole. Weyl spoke of one-dimensional tubes, a mathematical hint toward connected topologies. Later, John Wheeler coined the term wormhole, popularizing the vivid image. Missner and Wheeler described handles in space that physicists might call wormholes. Through the mid-century, mathematicians and relativists explored topology, embedding diagrams and black hole solutions. Early solutions like the Schwarzschild metric revealed bridges that later came to be called Einstein-Rosen bridges. Modern researchers, Visser, Thorne, and others, formalized traversable wormholes and their energy requirements. Key milestones: Flamm, Einstein and Rosen, Wheeler, Morris and Thorne, then Visser, each added pieces to the picture. Terminology can be geometric or topological. Einstein-Rosen bridges, Ellis wormholes, Morris-Thorne constructs. Topologically, a wormhole is a region whose interior is not simply connected, a handle in space-time. Next we examine types of wormholes and the metrics that describe them in detail. The Schwarzschild solution describes an eternal black hole. Its maximal extension includes a temporary bridge called an Einstein-Rosen bridge. But this bridge pinches off too fast for anything to cross. It's non-traversable in practice. Mathematically, the Schwarzschild metric encodes how space and time change near a spherical mass. Terms like r and t control radial distance and time. 2gmrc² marks the event horizon. Traversable wormholes, like the Ellis and Morris-Thorne models, are shaped so a traveler could pass through. One example metric shows a throat of finite radius. The math guarantees no singularity at the center. Keeping a traversable throat open appears to require exotic matter, energy that violates standard energy conditions. Quantum effects, the Casimir effect, can produce negative energy densities in small regions. Physicists name energy constraints: the null, weak, strong, and dominant energy conditions. Wormholes challenge these. In some modified gravity theories or extra-dimensional models, wormholes might avoid exotic matter requirements. Quantum foam might host microscopic wormholes that appear and vanish at the Planck scale. Microscopic wormholes could affect quantum processes, while macroscopic ones would need cosmic scale conditions. Metrics describe geometry. Energy conditions constrain reality. These mathematical tools determine what wormholes might or might not be. Next, can wormholes be used to travel space or time, and what paradoxes arise? A traversable wormhole would let you go from one mouth to the other without crossing an event horizon. To keep the throat open, calculations indicate matter with negative energy density is required in the throat region. The Casimir effect shows quantum fields can create negative energy densities between plates. Some physicists hope these quantum effects might be harnessed to stabilize microscopic wormholes. Kip Thorne and colleagues proposed a Morris Thorne wormhole held open by a shell of exotic matter. In theory, a person could traverse such a throat if energy conditions were satisfied and tidal forces were tolerable. Morris, Thorne, and Yurtsever showed you could convert a wormhole into a time machine by accelerating one mouth, or move one mouth into a stronger gravitational field. Time dilation creates a clock difference between mouths. Important limit: you cannot go back to times earlier than when the wormhole was first formed. Visser proposed a Roman ring of multiple wormholes that might evade some objections, but it remains speculative. Semi-classical calculations often show destructive feedback, virtual particles amplifying and destabilizing the machine. Some modern proposals link wormholes to quantum entanglement, the ER=EPR conjecture. Other ideas invoke many worlds. A time travel paradox might be resolved if returning travelers reach a parallel branch. Bottom line, quantum effects offer small negative energies. Macroscopic stable wormholes face serious theoretical and practical obstacles. Physicists continue to debate feasibility. Research explores limits of gravity, quantum fields, and cosmology. Next, we look at how wormholes appear in fiction and what they mean for our imagination. Wormholes are a staple of science fiction. They enable interstellar travel, dramatic visuals, and simple storytelling solutions. Common uses: stargates, shortcuts between galaxies, and time portals, each inspired by the core idea. Beyond fiction, studying wormholes probes fundamental physics, gravity, topology, and quantum fields. Discovery would reshape our understanding of space-time, but any claim would demand extraordinary evidence. Wormholes sit at the boundary of rigorous math and bold imagination, elegant solutions, thorny energy issues, and tantalizing possibilities. If you want to explore further, read Thorne, Visser, and recent papers on ER=EPR and quantum gravity. If you enjoyed this explanation, like and subscribe for more deep dive science videos. Thanks for watching.